So, welcome everybody to another episode of Software Architecture on Stream, this time around with Adam Tornhill. Adam, welcome to the show. Great to have you here.
Thank you very much. Great to be here.
Thank you. So, there is a note to the podcast listeners about today's episode. So today we are going to do, well, hands-on. So there's going to be a live demo. And I'm not sure whether it's going to be easy to follow through the live demo in the podcast. So we will talk about behavioral code analysis first, and then we will have that demo. So that's just sort of a disclaimer or a heads up. The other thing that I wanted to quickly say, so actually I did quite a few episodes about static architecture management where you would use tools to make sure that the architecture stays, well, sane and maintainable. And I think this is another episode that is pretty much along the same lines. So I will link to those episodes in the description. So much for the introduction. And our guest today is Adam. So, Adam, who are you and what are you doing? Can you say a few words about yourself?
Sure, I'd be happy to. So I'm Adam Tornhill. I'm based in Sweden and I'm a programmer. I've been writing code for like 3 decades by now. I still enjoy it. I still get to do it every now and then. My background is as an electrical engineer, but also happen to have my second degree within psychology. So that's one of my big interests. And what I've been doing over the past 10, 15 years is basically to take my psychological perspective and put it on top of my technical background. So a lot of the stuff we're going to talk about today, like behavioral code analysis, comes from that intersection of psychology and code. And I'm also the author of a couple of books. I wrote Your Code is a Crime Scene 10 years ago. There's actually a second edition coming up in just a couple of weeks. And I'm also the author of Software Design X-Rays, which is much more about how do you build an efficient software architecture and how to ensure it's sustainable and maintainable from the team perspective. So that's pretty much me.
Yeah, great. So actually that makes it 2 psychologists in a row because we had a psychologist last week too. So that's quite interesting. So you already said this episode is going to be about behavioral code analysis. So what is it and what's special about it?
So behavioral code analysis is based on the fundamental fact that we're never, ever going to be able to understand a large-scale software system through a static snapshot of the code. It's just not possible because the most interesting information isn't there. So in a behavioral code analysis, we say that the code, the way it looks now, is important. It really is. But it's much more important to understand how the people behind it, the software organization, how we interact with their system we're building, and how we collaborate with each other. And behavioral code analysis is very much based on a data-driven approach. So all of these things are possible to measure and reason about objectively. So that's like the short summary.
Yeah. Thanks a lot. I think that was short and crisp. So why would I care about it?
Well, there are multiple reasons. So I can start from my personal experience. The reason I start to work with behavioral code analysis at all is that in the past, I used to be a consultant. And quite often I was hired in some kind of technical leadership position, which could be something like a software architect, it could be a lead developer, tech lead, so on. And as part of that job, what I constantly had to do was to communicate between the engineering team and the non-technical stakeholders. And when I say non-technical, I don't mean that they don't understand technology. It's just that their primary job is not to write code. It could be product people or business managers. And what I very often found myself doing was to say, no, we cannot go ahead with that feature because the code is a mess. We need to clean it up first. And those discussions were extremely hard to have because code is hard enough to understand for a developer. And it's virtually impossible for a non-technical person to kind of peek into our world of code. So I started to use a bunch of static analysis techniques to kind of try to put some numbers on the technical depth that I found in source code. And it turns out that the moment you go to a product person or a non-technical stakeholder and you tell them that, hey, we have to refactor this because it has a high cyclomatic complexity. The moment you say that, you're going to lose them. They're never, ever going to talk to you again. So I was looking for something more friendly and also something more impactful in terms of business. Because the thing with technical debt is that there is so much of it and we cannot fix all of it at once. So I was looking for ways to kind of prioritize it from a perspective that means something to the business. So that's when I kind of started to look at, okay, how does the organization work with the code? Because this is information that we can actually pull out of systems like Git and other version control tools. So if I could figure out where the organization works, then also get a different lens through which we can view the code base. So we know that, okay, the parts that are being worked on frequently, those are parts that have a high interest on any technical debt. So that's one reason. The second reason, I'm going to keep this brief, is that successful software is about much, much more than technology. It's also about having the right team with the right people and organized in a way that makes sense from the software architecture. And if technical debt and things like code quality, if they lack visibility, this social side of code is virtually invisible. And that's where behavioral code analysis can help to shine light on these organizational factors too.
So just a note from my side. So I listened to one podcast that you did, and in the podcast you gave the example of that team that was working on a project which was going well, pretty much fine. And then there was that other project that they had a hard time maintaining, and that was really hard to work with. And you said that you looked at the metrics and you figured out that actually that system was better structured than the other one that they didn't have any problems with. So even though the metrics were better, it was hard to maintain. And you in that podcast, you said that the reason was that it was originally done by a different team. And when we prepared the episode, you said that this is actually something that happens quite frequently, this kind of situation. So, and that was one of the motivations why I really wanted to do this episode, because this fact really drives home that just looking at the code doesn't really tell you whether it's maintainable or not. So I found that quite interesting, and I think it's one of the highlights about that podcast episode that I listened to.
Yeah, thank you. Yeah, it's a super important perspective, because it's really, really common that we mistake a lack of familiarity for complexity. And without behavioral code analysis, there's simply no way of knowing. And if you don't know what the real root cause of any particular issue is, a system sought to maintain, then you will solve the wrong problem, right? So it's very tempting to kind of scream for that redesign, that rewrite. But if the system is already good, then maybe what you really need is a proper onboarding. So I promise that I will show you some examples of this today as well.
Great, looking forward to it. So final question before we dive into the demo. So what is CodeScene? So
CodeScene is the company I founded back in 2015. And the reason I did this was that after writing Your Code as a Crime Scene, what I did was basically I described a number of behavioral code analysis techniques that I had kind of developed and used over the years. And they had worked really, really well for me, working with various product companies. I wanted to share them. But I kind of also understood that, if I want these techniques to become mainstream, and I really think we need them in our industry, then there has to be good tooling that kind of automates all these tasks. And there was also a lot of things that I really wanted to do, but I knew this is going to take years to pull off. So that was my main motivation for founding CodeScene. And CodeScene, what we do is we develop the CodeScene tool that you can use to automate all this stuff that I'm going to talk about today.
Cool. So before we jump right into it, Abduram Asik, I hope I pronounced that correctly, says, "Good to see you here, Adam, and thank you for the stream." So that's the first thing that we see in the chat. So shall we just jump right into the demo? Do you want to share your screen and then we take it from there?
Yes, sure. I'd be happy to do that. So I'm going to show a number of different use cases today. And the way I want to start by looking at a very, very important use case, and that is how do you manage technical debt properly? And the reason I want to start with that is because doing a good job at managing technical debt is like the foundation for everything else, right? If you don't keep technical debt and code complexity in check, it's going to be virtually impossible to succeed with good teams and so on. So let me share my screen and jump right into the demo. And I do look forward to take questions as we go along, so please keep them coming.
Yeah.
So here we go. You should be able to see my screen now.
Yeah.
And what we're looking at is an analysis. I'm using the CodeScene tool for this, of course. But the system we're looking at is MongoDB. It's on a document database. It's pretty well known. Most of you are probably familiar with it. And there is nothing special about Mongo at all. The only reason I'm using it is because I'm somewhat familiar with the code base. I also think it's representative of what the code base looks like in our industry. So we see here that Mongo consists of 1.2 million lines of code. So I would say like a mid-sized to large-scale code base. What's also interesting is that Mongo is developed in multiple programming languages. So we see there's a lot of C++ code, some plain C code, JavaScript, of course, and some Python. There's always Python in all code bases, and then the occasional scripts. So anyway, my point is that if you have a code base that consists of 1.2 million lines of code, who can get a holistic overview of that code base? Who would know inside the organization where the strong and weak parts are? And even if you know that today, how do you know that the same truths apply tomorrow or a month from now or a year from now? It's virtually impossible for a human to grasp code at this scale. So the first thing I want to show you is how behavioral code analysis can help you get situational awareness of a large code base. So we have this dashboard. I'm not going to go through it now. We're going to return to it later. But first thing I want to do is to visualize the code base. So let's see what 1.2 million lines of code looks like. Here we go. So this is a type of visualization that I've been using heavily. It's called enclosure visualizations. And the way it works is that if you look here at these circles that I'm hovering over right now, then each one of these circles are a top-level folder inside this repository. So that means that if this was your own code base, then we'd recognize the names of these folders as like important subsystems or high-level components. It's also interactive, so I can click on it and I can zoom in, and then I can reveal the subfolders beneath it, right? So it's completely hierarchical, always follows the structure of your code. And once I get to the lowest level of detail, then I see each file with source code here as a circle. And you see they have different size. Some are quite small, others much larger. So the size of a circle just reflects the number of lines of code. So the larger the file, the larger the circle. Mm-hmm. And lines of code is a super rough metric, but it's a pretty good approximation of how big the potential problem is. So anyway, the important thing here is the color of the circles, because the colors reflect something that we call code health. And that's what you see here on the right. So let me give you a brief explanation of what code health is. Basically, what I was after was a way of figuring out if a piece of code is easy to understand or if it's complicated. And I kind of approach this from the perspective of the human brain. What type of coding constructs make code hard to reason about? And this is a concept we've been working on for 5 years now. So let me switch over to this one. Here's our documentation. And I want to zoom in a little bit so you can see it. Is the text large enough?
Yeah, I think it should be fine.
Yeah, let's try. You don't need to see the source code to the left. It's just like a schematic illustration. Mm-hmm. But anyway, if you look at the research that's been done on things like program comprehension and code complexity, you will quickly figure out that there's not a single magical metric that can capture a multifaceted concept like code complexity or code quality. So what we do instead is that we measure a whole palette of things. We measure like 25 different factors that we know that these things, they actually impact our ability to understand code. And the way it works is that you take a piece of code at file level, you parse it, and then you analyze the resulting parse tree for various examples of unhealthy code. And you see some examples here. It's not the full list, but just to give you an idea, that we look for things at the module level, things like cohesion, right? Do you have one responsibility in that file or multiple? At the function level, we might look for things like brain methods. which are like these overly long and complicated functions that tend to be central to a class or module, so that each time you add a new feature, you end up in a brain method, and over time it just becomes even more complicated. We also do some copy-paste detection to discover things like missing abstractions and drive violations. And of course, at the implementation level, we look for various complexity smells. And the one I want to highlight is deep nested complexity, which is like, if statements inside if statements inside if statements, and then a loop for good measure. That's really, really driving the cognitive complexity, and it's like an open invitation for bugs. So anyway, we scan each piece of code and look at what do we find here. Then we have the algorithms that can take the results of that. It can kind of score and aggregate and categorize every single piece of code as being either healthy green code. That's where we want to be with the majority of the code. And again, green doesn't mean perfect. It just means that it's low risk for a developer to work with this code, and it's fairly easy to understand. So green is acceptable. And then the next category, the yellow-orange category, that's when you have started to take on technical debt. The code is now hard to understand. And unless you're careful, you end up in the red category, which means that, this code is extremely high risk. And I've made a couple of claims now that, code is expensive and so on. And the reason I can make those claims with confidence is because these colors that you see here, they actually carry some meaning. Because what we did, and I say we, it was me and my colleague, Marcus Borg, a software researcher, we sat down last year to actually study how does code health impact the business. And what we did was the following paper. So this is a white paper called a Code Red paper. You can probably get the link after the stream. And what we did here was that we looked at that, okay, what's the difference between these various code health categories? And we looked at it from two different perspectives. The first was speed to market perspective. And we saw, and you see that in that top graph here, that if you have green healthy code, you can be more than twice as quick when implementing features or fixing bugs compared to red code. So this is a very clear competitive advantage. If you manage to keep your code bases clean, then you can be twice as quick as your competitors who are in the red or even yellow category. Mm-hmm. Another interesting thing was that we kind of also realized that, looking at averages is interesting, but there's more to it. So if you look at the second graph here at the bottom, what we did now was that we looked at, okay, what's the variation? Is it the case that it can take much longer in red code, or is it pretty much a linear relationship? And what we found here is super interesting. When looking at the maximum time you need for making a change to code, it turns out that green code is very predictable. The maximum time it takes to change a piece of green code is very close to the average time, right? So it's predictable. For red code, all bets are off. Making a change to red code can take an order of magnitude longer than changes to green code. So this can be really, really stressful to a business. I mean, imagine your manager having promised a particular feature to the sales team, right? And you think you can have it in 1 month, but it could actually take 9 or 10 months. That's going to put a lot of pressure on everyone. Mm. So red code is disastrous to team morale and stress. And finally, the last thing I want to show is that the way we calculated this was that we connected to code bases from, I think we had 39 companies on board. We also connected to their Jira dashboard, so we can kind of calculate these times in development. And since we had access to Jira, we can also calculate the number of defects. And if you look at this graph, you see that red code has on average 15 times more defects than green code. And this is something that translates directly into the product maturity experience. So red code is like the killer of IT projects. So I hope I managed to explain that. Are there any questions so far, or you want me to go ahead?
There is a technical question. So if you go to the homepage, how do you look at the stream in full screen? And the answer is, if you go to the homepage, you can view the thing on the stream on YouTube, and then you can use at the bottom right, there is an icon that allows you to go full screen. So that's the question there. Basically, if I understand correctly, you did empiric studies that actually say that these red code things do have a business impact, as in it takes longer to do changes there are more defects and so on. So just eliminate all of them. Is that what I should be doing, or what's the idea? What's the sort of action that I should take?
That's a super interesting discussion point, because this is exactly where behavioral code analysis comes in.
Okay.
So if we all agree that kind of, yes, we did empirical studies, formal research, everything you saw is statistically significant. So what this means is that when we see something red here, we know that, okay, this is a problematic area. It means that any features that touches this code are going to be risky. And this is, of course, something I can use up front as part of my planning, right? But how do I go about this proactively? Do I just jump at all those red areas and eliminate them? Well, you shouldn't really do that, because if we look at these red areas, if I click on them, let's pick this one, for example. I see that this one alone consists of 6,000 lines of code. This one is for almost 5,000 lines of code. So there's lots of code, right? And as a business, you simply cannot spend 2 years just refactoring your code base, right? You need to balance it with delivering new features. So we need to be smart about where do we target refactorings and improvements. And this is where behavioral code analysis can help. Because if this was the only picture I had, then, I mean, I would have to guess. I would have to make qualified guesses. Where do I fix the tech debt? What I can do now is I can look at the different perspective. I can look at something called hotspots. And if I click here, you see the color changes. So let me explain to you what you see. And I want to explain to you by going to our descriptive graph here. We're going to return to this map very soon. So I want to look at this particular curve. So what you see here is a different summary of this code base, Mongo. On the x-axis here, we have each file in the code base. So we see there are 3,500 files. And these files are sorted according to change frequency. And that's what you see on the y-axis. The change frequency is simply a measure of how many commits have the development team done to this particular file, right? So something we pull out of Git. And as you see here, this distribution forms a power law shape. And I can zoom in at the head of the curve here. And I can see that most of my code is actually in the long tail. So that means that's code that's rarely, if ever, touched. So if I have some red code in the long tail, I want to be aware of it because it can be a potential long-term risk. But it's most likely not an urgent thing, right? So what I want to do instead is to focus on the head of the curve where I have most development activity. That's the part of the code that I really, really need to keep green. And this is where hotspots come in, because hotspots help you identify those parts of the code. So the way I go about selecting refactoring targets is that I can typically start from the code half. And I typically have some knowledge, some domain knowledge that the REPL here, for example, in Mongo, it might be an important piece of code. So I zoom in on it. And then I see that, okay, there are like 6 red dots here. Which ones are hotspots? Oh, it's really just 3 of them. This one, and this one. So if I look at this replication coordinator info, I can now start to plan a refactoring that's much more data-driven. It's something I can communicate to the business. So first of all, I would say that, okay, this code is red. So I can tell them that, okay, it's going to be twice as expensive to change in it. We're going to have an increased risk for defects. I can also show that it's relevant because we have made 66 commits to this file just over the past year. So like more than once a week, some developers impacted by this. Finally, since we have access to Git, we can pull out the historical revisions of this file and measure the long-term trends immediately. So you see here that the code complexity in this file has grown pretty much over the past decade, and there's no sign that it's slowing down. So that's like the first step, how I prioritize.
So in that graph, how do I know that it's actually a change hotspot? I'm not sure whether I got that. So how do you know that what's the representation of something that is changed frequently? I don't think that you mentioned it, or I missed it.
That's what I call a hotspot. It's a development hotspot. So the more red something is, the higher the development activity, the further at the head of that curve it is.
Okay, so it's the color. So color changes semantics from from pointing at a problem to pointing at a hotspot.
Yeah. And I could, of course, cheat as well, because there is a list of them in CodeScene already, right? So if we ask CodeScene, we're going to be able to pull up a list of, okay, what are the most problematic hotspots here, right? So I can immediately see them. But I always find it's easier to start to reason about behavioral code analysis when looking at the visualization. Then, yeah.
The other thing, so that's a statement about the past, right? So it says this is what has changed in the past, and you're basically predicting that sort of the hotspots will stay the same. Is there some empiric studies about that, or how do you know that the future is going to be like the past? I mean, obviously there is a strong tendency, but is there any? Are you aware of any data or any exceptions from the rule in that regard?
Yes. So there are. Let's address the most burning question first, perhaps. So there is some pretty solid research on this. There is, of course, a risk for false positives. So one thing that could show up as a hotspot, to give a pretty common example, is if you have something like version.txt, right? That's stepped each time you do a release. That file is going to pop up as a hotspot.
Right.
So what we did in the CodeScene is that we automated a lot of patterns so we can kind of detect and automatically exclude these false positives. But at the end of the day, it's you as the expert on your system, because behavioral code analysis or CodeScene is not trying to tell you what to do. It's there to kind of, support you with data and evidence so that you can make decisions based on data. So at the end of the day, you typically know that, okay, yeah, this module, it might be a problem now, but we plan to replace it in, 3 weeks. What you do then is you tell the tool about it. So you go to that hotspot and you say that, okay, I'm not going to do anything about this. I don't want to see it anymore. Then it disappears. Or you can tell the tool that, yeah, this is a real problem. We need to refactor it. And in that case, CodeScene is going to measure and make sure that you meet your goal.
Okay.
So what I want to show you is that if you have a lot of hotspots like this and you have a lot of code health issues, then you can also ask the tool to prioritize them for you. So if I click on Refactoring Targets, we can actually take this large code base of 1 to 2 million lines of code and narrow it down to just 3 red hotspots, where CodeScene says that based on how you as an organization work, these modules seems to be the one that drive most of your technical costs. And the way we do that is by looking at, okay, how many developers are impacted by these files, right? The more developers that work there, the more expensive. And what does the dependencies look like? If I change that file and also have to make cascading changes to other parts, then it's a cost driver, right? So stuff like that. So what I can do now is I can click on one of these. So let's pick this one, Replication Coordinator. Sounds very central to Mongo. So if I click on it, then I see the data we saw before. And I also see that this is a really large file. So it's almost 5,000 lines of code. And refactoring 5,000 lines of code is going to take a long time. So we need to prioritize even deeper. And what I do then is I use a behavioral code analysis technique I call X-ray. So if I click on the X-ray here, what happens now under the hood is that we take this large file, we parse it into separate functions, and then we look at the Git log to see where do each commit hit over time, and we sum that up so that we get development hotspots at the function level. And this is what I very often use as an actionable starting point for refactorings. So to give you an example from this file in Mongo, Replication Coordinator, I see that the number one hotspot and refactoring target at the function level is called finish load local config. And I can see that the second one is start load local config. So to me, it almost looks like we have a hidden responsibility here asking to get out. And the way this list is sorted by the change frequency, which is the number of commits. And as you see, it descends pretty rapidly, right? So you can typically pick a small amount of code here, in this case, 147 lines of code, and start a refactoring, right? And it's a refactoring based on how we actually work. So I hope I managed to explain that.
Yeah. So there is one question in the chat by Ratis Naval. The question is how to know which is the factor affecting the code health. So I guess the point is that the code health is red, green, and yellow, but it's a sum of different things. So in particular, if you want to do a refactoring, you need to figure out which of those factors are actually causing it to be red. So how do you figure that out?
So let me show you. So let's go back to this visualization. Let's go for the refactoring targets. And we found a needle in the digital haystack here. So I click on it. What I can do now is I could, as you saw in the X-ray, I had a column called code review, which will tell me, okay, what are the code smells in this particular method? What I can also do is, if I want to know why this one is red and not green, what I can do is I can ask for a virtual code review. So if I click this one, then CodeScene does a full code review, and it shows you what type of code health issues did we find here. And we try to put a lot of effort into, okay, explaining what you see. So in this case, we see there is something called a bumpy road here. We always have a section that shows you where in the code do I have this particular problem. So we see all the functions, and this is a long list because it's pretty messy code. But then there's the most important section that explains why it's a problem. So this is where I explain how do we measure this? What is a bumpy road? Well, it turns out that the bumpy road is a function with multiple chunks of nested conditional logic. Okay, good. And then we also give recommendations on how to fix it. So everything from general refactoring recommendations to very specific refactoring recommendations based on your own code. How can you take the red code and turn it green? So this is where we would figure out what the code health issues are. So I hope I managed to answer the question.
Yeah, I think that's a good answer. There is a comment by some person on YouTube. It's just letters and numbers, their name. So, and they said you can tune SonarQube the same way. I'm not sure whether you want to comment on that. So Sonar is obviously that another tool for static code analysis, at least.
Yeah, I can. I mean, I often get asked that question because Sonar is quite widespread, and there are a couple of important differences. The first is that Sonar, don't want to bash Sonar. It's a very good tool for its purpose, right? If you want a lower level feedback loop when writing code, it's a really good choice. When prioritizing technical depth, it's simply outside the sweet spot of CodeScene, or it's inside the sweet spot of CodeScene, but SonarQube was never designed to do that. So if you look at the research that's been done on SonarQube, you will find that what they identify as technical depth and code smells doesn't correlate with delivery times or defects. There's no correlation between it. The other thing is that what's really important when it comes to tech depth is not to find bad code. That's usually the simplest part. What's really important is how do you prioritize it? And to the best of my knowledge, CodeScene is the only behavioral code analysis tool. So I hope I managed to clarify that a little bit.
Yeah, and the prioritization is based on the Git history, and I don't think Sonar even takes that into account, right? So no. Exactly. Okay.
And another thing that I would like to elaborate on is that I've shown you a lot of stuff now. Okay, how do you analyze a code base? How do you visualize it? But to really, to get the actionable starting point, what I would do if I would going to adopt these techniques would be that I would look at trends over absolute values. Because one of the big benefits of CodeScene is that we have access to Git history, meaning that already the first time you run it, you can start to see long-term trends. And you see here, for example, with code health, now we know what these different metrics mean. So we see that the hotspot code health is pretty low. It's problematic. The average code health is a little bit better, right? But it's even more important to understand where do we come from? Because if we have a code health of 7 and it was 5 the week before, then it's a massive improvement, something we can celebrate. If it was 8 the week before, then it's a disastrous decline that we need to stop. So you can kind of see the trend here, right, in code health in the code base. And we also implement our quality gates based on trends. So I can see here that right now in this code base, and it's real data, 9 hotspots are declining in code health. So not just any code, but 9 hotspots, right? So we know that these are likely to be relevant. And if I look at the list, I can see here the second one is a really good example. So if we look here at the index catalog, I see that a year ago, it was already problematic space. But then over the past year, it declined to a lower code health. And over the past month, it has slided even further down. So it's now in the unhealthy space. And this is something I would definitely act upon. Mm-hmm. So I hope that clarifies a bit.
Yeah. There is another question by Chris H. on YouTube, and his question is, does behavioral code analysis apply on model-based programming too? And he explains it further and says, since there is automatically generated code, and I could imagine every hotspot being a systematical code risk. So I guess what he's trying to say is that because you might have a code generator and that code might be a problem and a hotspot, you might get false positives.
Yeah, and basically it's possible to analyze anything as long as you have it in version control. That's like the only hard requirement. And behavioral code analysis as such is language neutral. The only thing that's language specific is a CodeScene concept, and that's the code half metric. But in my book, for example, Your Code is Crime Scene, what I do in the last chapter is that I go a little bit meta and actually analyze the writing for the book itself, because I had it in a Git repo, right, where each chapter was a separate file. So you can kind of see hotspots in the book, right? So you can analyze any content. It doesn't have to be native source code. So you could, for example, analyze the input, your models, because I think they are persisted in some kind of XML format or something like that on it.
Yeah, I think the question really is, so if I do code generation, then every time I do the code generation, the code will be overwritten, so it becomes a code, a hotspot, and it becomes a false positive. And I have to admit that I'm not sure whether that's really the case, because, I mean, you shouldn't check in generated code, right? So
you really shouldn't, but I find that all the time. I mean, I've found code bases that have the complete node modules checked in, right? So it's quite common. What you do in that case is that most likely CodeScene is going to be able to detect and discover that this is auto-generated code, so it will automatically exclude it. If not, then you can tell the tool about it and say that everything under the generated folder is generated, get rid of it, and you won't see it.
Okay, yeah, I think that's a good answer to that question. There is another question that I have in the back of my mind. So it seems that this is something, if it seems like a natural next step after we did this analysis, or you did this analysis, would be to have a meeting with the developers or with some people from the project and talk to them about the results, about what you think is going on there, what the tools told you, to get some feedback about how that relates to their experience. Do you think that makes sense? Is that something that is really valuable and that you ought to do, or is it something that isn't that valuable after all, to communicate the results and to get some feedback from those developers and to get their opinion about it?
I think it's super relevant, and I think it's spot on, because after all, the way I describe CodeScene is I view it primarily as a communication tool. So what it allows us to do is that it enables all these conversations around, okay, what's actually happening to the system we're building? How are we working with it? And to give you an example on what works well is, I think bringing CodeScene up in a planning meeting and having those visualizations is really, really useful, because now you know that we have 5 important features that touches this area with yellow and red code. So we can either go ahead with those features because they are so important, but now we know about the risk, right? This could take 10 times longer. It can have all these defects, so we can kind of anticipate that up front. So it will be a calculated risk. But in the best of all worlds, we'll go back to a drawing board and say that, okay, let's instead spend some time refactoring, improving this code so that we can implement all these features safely, right? So we can have these conversations. And what's also nice is that you can actually make a business case for refactorings, because we know about these code red findings and they are visible in CodeScene too. So if you go to a delivery tab here, you can see that delivery is a combination of how long do you need in time in development and how much of your work goes through as unplanned work. Unplanned work is basically, post-release defects or production crashes. And we can see that here for Mongo that we have 31% unplanned work. If we look at the industry baseline, we see that that's pretty high, right? High-performing teams can deliver less than 15% unplanned work. So maybe there's room for improvement here. So what I can do now, So
how do you figure out whether work on the code base is unplanned? I mean, obviously you can't listen into the meetings.
No, we can't. So we base this on Jira issue types and tags and labels. So when you set up CodeScene, you have to tell CodeScene what's unplanned for us, right? And it has to be reflected with some kind of tabs. The rest we can calculate automatically. So time and development is something we calculate automatically.
Okay.
But the point here is that you can now, any improvements you do can come with an expectation to the business. And this is something that kind of helps get acceptance for improvements too, right? Because if I tell my product people that, we have some problematic hotspots, let us refactor them, then we can actually see the kind of the return on investment here as delivery would improve, right? We'll be able to deliver quicker with fewer defects. Mm-hmm. So that's, I think, something that's really important. Yeah. Another thing you can do is you can also have these conversations, break them down to a team level, because that's where you tend to make them actionable. So if you have multiple teams, let's say I'm on the query team, and I select query, and I now get the personalized dashboard for my team. And again, this is possible thanks to the behavioral aspect where we know which developer have written which piece of code, which we can kind of then aggregate into teams.
Mm-hmm. One thing, so I think you already mentioned it twice, that you can use these kinds of metrics and information to predict whether the implementation of some story will be high risk or low risk. But I guess that is something that I have to figure out myself. So basically, I have to talk to a developer, or a developer has to figure out, okay, we are going to touch this, and this, and they are all red, so this is going to be quite risky. Or is there some support in the tool for that?
And that's good. There is actually some support. So let me move over to another code base. So let's leave Mongo now. I'm going to torture another code base. I'm going to pick this one. So this is a code base from Microsoft. This is ASP.NET Core MVC. It's like a framework for building dynamic web applications. Most of it is written in, as you see here, it's written in C#, most of it. If we take a quick look at its code health, we can immediately tell that, yeah, there seems to be, first of all, it's interesting to note that there's almost twice the amount of test code compared to application code, right? So they've invested a lot into automating tests. And that also means that we need to make sure that those tests are easy to maintain, because otherwise they will become a cost sink. And also see here that there's only one red module. Here is something called default HTML generator. And what I can see now, when I hovered over it, was that something happened. If I hover over it, what I see now is that if I modify that file, we have a predictable and likely modification in 4 other modules. How can CodeScene know this? Is it some kind of dependency analysis? It is, in a way, but it's a behavioral dependency analysis. It's something I call change coupling. And the way you calculate this is that you look for patterns in the Git commits. So if a developer that makes changes to a default HTML generator modify a bunch of other files together with it in every single commit that they do, then we know that there has to be some logical dependencies between these modules. So change coupling is about things that change together, right? So it's the dependencies that actually impact you. And this is something I've been using a lot when reasoning about the cost of change. So let me show you some examples. Let's switch over to the hotspot perspective so we can see where the action is. Here's something interesting. So I'm now inside the test folder. So these are all automated tests. And here are a bunch of integration tests that I'm hovering over right now. And we see that one of them is pretty large. So what happens when I modify that test? Well, I see that I have predictable changes to like 6 other test modules. And now I can kind of dive through that lens and see, okay, does this really make sense? Or could it perhaps be that I haven't really encapsulated things as well as I expected, because this looks expensive? And it's always, you know how it is with tests, particularly with integration tests, that might be run infrequently, right? Or take a long time to run. That if you forget to update one of them, you're going to have a broken build, and then you kind of need to context switch and go back and fix it.
So what you're saying is that change coupling would support me in figuring out if I change something, what else will also change, and that's how I can reason better about changes that I needed for implementing some story.
Exactly. And it's something I use all the time for that purpose. It's also something you can use for things like legacy modernization. Let me show you another thing that I like.
I just want to emphasize, I think this is just a so very important point, because oftentimes in software architecture we focus on dependencies, and dependencies are fine as long as there is decoupling. So if there is a change to one thing and the other thing that is dependent on it doesn't change, that's fine. So you have to really figure out whether there is change coupling, and it's not enough to just figure out whether there's a dependency. And I fear that oftentimes this is neglected. So people just look at some diagram and say, okay, this depends on that, so that's a good or a bad thing, and really it should be about change coupling. So I just wanted to emphasize that. There is one question in the form on the website which I found interesting. So how do you know who is a member of which team in MongoDB? Because you said, the query team and so on. So is that open knowledge? I mean, is that something that people know?
Yeah, well, so on Mongo, this is a demo project, right? So here we kind of just made up the teams, but in a real real world setting, you know what your development teams are. So you might have, I don't know, 5 different Scrum teams, right? So you know who those are. You might have 3 stream-aligned teams. You know whose people are in which project. So that's something you need to tell the tool. We cannot know it. We know the contributors. But the nice thing is that you can automatically, since we know who's committing code, we can automatically kind of take those individual contributions and aggregate them into those teams. So when you filter by team like this and get the personalized view, it's actually a deep link. So if I click on visualizing this code base, what I see now is that it's all filtered by my team. So now I can see the red code for the query team. And I can also see if we have any hotspots in the query team. So this is something that you can use for things like retrospectives and so on. It's very, very useful to kind of bring it up as a backdrop that, okay, this is the way we have worked with the code base in our team, and I don't have to see everyone else's code.
So in this case, I'm looking at the code that this team actually modified, right? That's what you're saying.
Exactly. Okay, so you have this filter by team. So you can say, okay, what has the query team worked on? And this is what I usually use for planning.
So there are a few other questions. So one question is, does it work for G-test, whatever G-test is?
G-test? I don't know what G-test is, unfortunately.
Okay,
as long as it's in version control, it will work.
Yeah, I just G-test. There is Google test. So yeah, okay. I haven't heard about it either, so I'm with you in that regard. There is another question by that person with the number and letters, and they ask, what if you have a release branch and all of that commits are squashed? How do you determine the rate of change?
You don't really, because the thing with squash commits, I think they deserve special mention, is that squash commits are perfectly fine as long as they're used sensible. So if you work on a particular feature and then you squash a couple of commits, that's not really a big problem. The problem with squash commits is when you squash things that are unrelated to each other, like multiple features, multiple bug fixes, contributions by multiple people. Because the moment you do that, you kind of rewrite history. And we kind of learned from George Orwell, that's not a good thing to do. So I strongly advise against it, because you're erasing the information. There's no way of getting it.
Yeah, it's basically garbage in, garbage out, right? I mean, if you feed the tool some bogus history, it's gonna be bogus. Okay, sorry to interrupt. That's it for the questions.
Yeah, no, I'm really enjoying these questions. So yeah, I want to show you something else. We discussed the change coupling concept, how important it is to be able to reason about something up front. And I want to show you something a little bit more extreme. So this is another code base I've been looking at a lot lately. This is Telegram for Android. And we see here that it's a pretty large code base and a couple of million lines of code. And we see that from a code-off perspective, it seems a bit problematic. There's a lot of red code. If I look at the development activity, I see that there are some very clear development hotspots. So that means that if I work on this code base, it's very likely that I'm going to have to touch one of these hotspots sooner or later. So what I can do now is I can simply see, okay, what happens then? And I see it's some pretty tight coupling here, right? And this is also something that's really useful if you do something like legacy modernization. Maybe you want to kind of modularize a complicated code base, right? You want to break out separate components. Maybe you even want to break them out into services. Then it's really important to know what happens when you start to pull in one of these things. So now I know what type of dependencies I need to focus on first to kind of decompose the code before I start to pull it apart.
Mm-hmm.
All right. I would like to talk a little bit about this socio-technical intersection too. Do you think it's a good time to go there?
Yeah, there was one remark, I guess, again, concerning squash commits. And they said that, well, it keeps the history clean and you can roll back features on prod branches.
Yeah. So the way I prefer to roll back features is via feature toggles. I think it's a much cleaner way. And again, I don't think it's a problem if you squash code for individual features, as long as those commits related to that feature are really related. They're not including any bug fixes or something else, and they are done by one person. Because the moment you squash commits for multiple people, you kind of, you erase a lot of important and valuable history.
Yeah, I think it makes a lot of sense. Also, you want to, I would argue that you really want to, at one point, decouple new deployments from bringing new features into production. So you want to bring code into production that already has the code for a new feature, and then you want to toggle it on at one point, because otherwise it's hard to meet deadlines for specific features and these kinds of things. So I would agree, and I think that's another reason. Okay. Yeah, so go ahead concerning the socio-technical stuff. Looking forward to it.
Yeah, and I want to focus on one use case here in particular. I want to focus on knowledge, because we can actually start from Mongo here. If I click on it and I go to a dashboard, I'm going to remove that TIM filter. If I go here, knowledge distribution. So as I said before, it's not enough to have a healthy code base. It's really the most important thing, because it's the foundation for everything else. But it's not enough in isolation, because we also need to make sure that we have the right skill set inside the team and the right team. And this is something that changes a lot, because looking over the past years, we had a really high staff turnover in the IT industry. And the question is, of course, what happens if a number of key persons leave a project? We will still be able to maintain the code base. And this is something that's known as the truck factor, or the bus factor, or my favorite, the lottery factor, right? How many people can leave before your code base becomes unmaintainable? And if we look at Mongo, we see here that there's a decline in knowledge distribution. So we can see here, if I click that, okay, it seems that a couple of contributors actually left the code base, so we kind of lost knowledge. And we can see that reflected down here, that the code familiarity is 44%. So that means that 56% of the code will be written by someone that's not part of the current team, someone that has already left. So that's one aspect. How much are we familiar with it? The other aspect that I always keep an eye on is knowledge islands. So how much of the code is developed by just one person? And the reason I look at that, a low number like 3, that's really good, because it typically means you have multiple people that have worked on all the parts of the code base. But if that number is high, then it's not good for anyone. Because if the wrong person goes on vacation, everything kind of stands still. And it's not particularly fun to be that key person, right? You will be texted all the time. So what I want to show you is on a different code base. I want to look a little bit at, let's pick this one, React. So now I'm in a more detailed view. So you're probably familiar with React from Facebook, or UI library, quite popular these days. And I see that this code base, what's so interesting about it, it's a popular open source project, right? So I've seen the author statistics that there have been more than 800 people who have contributed code here.
Right.
And, as a manager, it's easy to think that with 800 people, if I lose 5 of them, it won't make any big difference. So let's find out what the real truth is. So now I want to show you a different view. I'll click here. And we'll see here is the same visualization of React that we looked at before, right? So I have the different sub-packages here. The main difference is that the color carries a different meaning. You see that most of the code is blue here. So blue means that the majority of the code is written by the current team. So somewhere in the organization, we would have someone that wrote each piece of code, right? And I can go and ask them, I can go talk to them. So that's really good. What I want to do now is to demonstrate how sensitive most code bases are to the truck factor. So what I'm going to do now is I'm going to pretend that 2 people leave the team. I'm going to pretend that Andy here leaves the team. And I'm also going to pretend that Brian leaves the team. And what I see now is that if these 2 people leave, the truck has actually hit us because we now lost control of more than 50% of our code. So we see everything that's red. That means that the main developer behind that piece of code is gone. And the question is, of course, that if you have a low truck factor like that, what do you do? Well, it all ties back to where we started with technical debt, because having a healthy code base means that it's also cheaper and easier to onboard people. When we look at our research, we see that onboarding a person in green code is more than twice as quick as onboarding someone in yellow code, right? So there's a big benefit to having healthy code. And what we can do here is that we can highlight specific parts of the code that need extra attention. So you see these dashed borders around some of the circles that's used to indicate an offboarding risk. And the way we know it's an offboarding risk is because we combine these social metrics, who wrote which piece of code, with the technical metrics. Is this a hotspot? If yes, then it's relevant. Does it have low code health? If yes, then a risk. So very often I use data like this to drive our factorings too. It doesn't just have to be code complexity, right? It can also be key person risk. Okay. So I hope I managed to cover this use case.
Yeah, I think that made a lot of sense. So there is one question from Oliver Drotboom, and he asked, is there a way to teach the 2 logical units modules to be able to correlate info you display scope to those? So I guess all the circuits that you're showing are directories of source code. So and the question is, I guess, whether you can replace those directories of source code with some logical module where you say, okay, it's this part of the code plus that part of the code and so on.
Yeah, you can. And it's really, really interesting because at some level, we want to be able to reason about the system at the level of architectural building blocks. So to show you an example, what I have here is another project. This is Spinnaker from Google and Netflix. And each one of these bubbles, interestingly enough, is a separate Git repository. So you see here that you can analyze multiple repos. It's also claimed to be a microservice-based system. I would say it's at least service-based. So what I would like to do is I would like to see this analysis at the level of services. And because it's a complex system, not only is it large, but if I look here at program languages, I see that to the right, it's written in lots of different languages, right? So I can reason about this. What you do is you simply tell CodeScene that everything below this folder and that folder, that's part of this component, right? So you kind of map up your file system. And when you do that, then you can actually see hotspots at the level of your architecture. You can also see the code health at an architectural level. So now each bubble represents the whole system. Okay. And the use case I find particularly interesting is change coupling. We already discussed it at the file level, but if I go to the architecture level, I can actually see the coupling between different services. And I can even overlay it with the team information so that I can find dependencies between different teams. And these are the type of dependencies that tend to be really, really expensive. So I want to be aware of them and make sure they evaluate them to make sure they make sense. So I hope I managed to clarify.
Yeah, I think that was spot on. So we are pretty much at the end of that hour that we planned for the stream. So we've seen all these concepts and we've obviously seen the tool, and it's very impressive. So what shall I do differently on Thursday?
I think that what I recommend is that you try to analyze your own code, because it's one thing to see all these open source examples, but once you see it in your own code, you can immediately get these insights because you have all the context. And it's actually free to use on your code, right? So CodeScene is free for open source projects. you have to pay for closed source code bases, but you can run it for free for 2 weeks and have full access to a tool. So you can kind of build these maps and you can kind of use them to communicate and see if they can help you get situation awareness of something as complicated as code.
So the idea is to take the tool, use it on your code base, and then have a nice meeting and a nice chat about it and see what comes out of that. So I think we've answered all the questions. Thanks a lot for taking the time. Thanks a lot for the demo. There are no more questions coming in, so thanks a lot. And yeah, we will put some links to the paper and to the code to the tool, obviously, in the show notes. So you're welcome to look at them. And yeah, have a great day and see you next week. So there will be an episode next week on Friday, and I guess the information will be out on Tuesday or so about what's actually going to be covered there. Okay, thanks a lot.